So we have discussed how to find order of reaction by the given data. So then today we are going to discuss how to find order of reaction by using half-life. So we are going to find order of reaction by half-life method. Okay. So basically, uh, what is half-life? What is half-life? Half-life means that the time at which the concentration becomes half. Half-life means the time at which the concentration of a reaction becomes half. The time at which the concentration of reactant becomes half. Okay. So you would be given a graph, and sometime they would be giving you a value, a whole data, and then you would be making your graph. And then after making the graph, then you would be determining, after calculating the half life, you have to calculate more than one half life so that you can decide that what is the order of reaction. So if the first half-life is equal to the second half-life, if the first half-life is equal to the second half-life, so you will say that the order of reaction is first. Like this is first order reaction, okay? If you are going to calculate half-life by, if you are going to calculate order of reaction by using half-life, so then uh, you will be calculating the two half-lives, and then you would be comparing. So if you can see that the first half-life is equal to the second half-life, so you can say that this is first order reaction. So this is your first order reaction. Okay. And if you have zero order reaction in which the first half life would be greater than the second half life. Okay. And for the second order reaction, you will see the first half life would be greater than the second half life. So let me write it down that if you have uh, first 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 half life is equal to the second half life, first half life is equal to the second half life, so that would be your first order reaction. Okay. And if you can see, like the first half life is greater than the second half life, okay, first order, then you can see that the first half life is greater than the second half life. So you can say that this is your zero order reaction. This is your zero order reaction. And if you can see, like the first half life is less than the second one, this is the second order. That's it. Okay, this is your second order reaction. So, uh, so this is very important because this would help you a lot in finding out the you can say order of reaction. So you would be calculating the half-lives. Okay, so let's suppose this is the curve in which this is your initial value, that is 1, then this is 0.9, and then concentration is going to decrease as you go down. So since the concentration is 1, okay, so the time at which the concentration becomes half, So the half of 1 is zero point 0.5. The half of 1 is zero point 0.5. Okay. So exactly the concentration becomes half. It's changing from 1 to zero point 0.5. It's changing from 1 to zero point 0.5. So now I can see the time. So the time is 3.8 seconds. So the time is 3.8 seconds. Okay. This is your this is your time at which the concentration becomes half. Now I'm going to find out the second half life. Okay. So the half of zero point 0.5 is 0.25, and the time at which this concentration becomes half is this, that is 7.5 seconds. This is your second half life. So now what you have to do, the first half life was 3.8 and the second half life is 7.5. Okay. Now you can see that the second half life is greater than the first. When the second half life when the second half life is greater than the first, that reaction is second order. That reaction is second order. So in this way you can calculate the order of reaction. Since this is from the past paper, they have given you the whole thing with with ready-made line. Okay. So what you have to do, you are only supposed to do to calculate the order of reaction by taking first and second half life. After taking first and second half life, you would be comparing with like the two half lives, and then you have to decide that what is the order of reaction. Okay. So this is the half of zero point 0.2, and I have taken time, that is 62 seconds minutes, sorry. Then the half of zero point 0.1 is 0.05. So the time at which the concentration becomes half is 125 minutes. I'm going to subtract so that I can get the second half life, that is 63. The first half life was 62 and this is 63, almost they are the same. So I can say that the reaction is first order. Since the first half life is equal to the second half life, it's plus minus 4. Okay. If this would be 64 and 62, so I would be considering that they are the same. If 65 and 62, I would be considering that they are the same. Okay. So this is your first half, this is your first order reaction after taking the different half lives. Yes.
Sir, I don't understand why we subtracted.
Yes, okay. So if you have calculated the first half life, that was 62 minutes, okay? So obviously now you're going to take another time. So this was your first, okay? If you're going to have 125 minutes, this is the total time. This is the total time. I need to get this time, man. I need to get this time. If I need to get this time, so ultimately I have to subtract this time from the total so that I would be getting the second one. This is the reason I'm going to subtract the total minutes from the first half life so that I can get this. Are you getting me?
Yes, sir.
Exactly. So, and this is the formula you will see in your paper 5 as well. T half is equal to 0.693 over the rate constant, that is this, and then you can calculate the half life. Okay, this is the relation that you may use if needed. Okay, and then you can see, if you can see this type of graph, okay, in which each half life is exactly half of the previous half life, you can see that the half life is going to decrease. As you can see, the half life is going to decrease. The half life is going to decrease. Concentration of reactant decreases as the time passes, but the speed with which it's decreasing, it remains constant. Like the slope is like the gradient is constant. So therefore, zero order reaction. For zero order reaction, concentration of reactant decreases, but rate remains unchanged. Rate is constant. Since the line is straight, rate is constant, it's constant. So gradient remains same. So I can say this is zero order reaction. You can predict the order by looking at the graph. It's concentration versus time. I have explained in the last class. They are the same thing. This is for the first order one, and this is for the second order. Okay. Uh, and then I told you in the last class that the remaining part we would be discussing in the next class. So the first portion was how to find the order of reaction by using the half-life, and this is called the reaction mechanism. That's very important. Uh, uh, how the you can say how the catalyst works. As you can see, most of the reactions have more than one steps or reactants. So let's suppose um, this is your reactant. Okay, this is your reactant, and this is your nucleophile. The nucleophile is going to attack on this, and nucleophilic substitution reaction is going to take place, leaving the nucleophile. Okay, so OH minus is going to replace this chloride ion. Ultimately, uh, rate of reaction is directly proportional to this. Why? If you are going to change the concentration of OH, so the rate would not change. So the rate would not change. You know why? Because this is the slow step. When the chlorine is going to, when the bond between carbon and chlorine is going to break down, ultimately this is the slow step. So rate depends on the slow step. Okay. So that's why I'm saying it's raised to the power 0, which is equal to 1. So if you're going to change the concentration of OH negative ion, nothing would happen because the rate is not depending upon the concentration of OH negative ion, but because equation shows overall reaction. You know, uh, same thing, same goes over here. I'm going to do the mechanism how it works. First of all, if you remember in AS, we used to discuss SN1 reaction and SN2 reaction. Okay, SN1 reaction we used to say that this would happen in 2 steps, and for SN2 reaction we generally say that this reaction happen in only 1 step. So it was inverse, like SN1 in 2 steps, SN2 in 1 step. So at that time, uh, we didn't tell you anything regarding 1 and 2, that why 1 and 2. 1 represents what and 2 represents what. Basically, that was order of reaction. You know why? This is the thing that I'm going to show you, that this is SN1 reaction. The SN1 reaction occurs in 2 steps. So in the first step, this bond is going to break down, and then this is going to be formed. So this is your slow step, because always when you're going to break down the bond, so it's always difficult. In step number 2, the new bond is going to form between this positive charge and this OH negative ion. So ultimately, this is the fast step. So fast step is called, like you can say that the slow step is the rate determining step. The slow step is the rate. Let's suppose I'm going to compile the result. Okay, I'm going to compile the result. We are three people. We are three people. Uh, let's suppose you are giving me envelope. Okay, you are giving me envelope, and I'm going to put your result card into the envelope, and I'm going to Sahil, and he is going to make all the envelope in particular order. You are doing very fast, Sahil is doing very fast, but I'm very slow. I'm going to take your time when I'm putting your result card into the envelope. So obviously, if you are doing fast, if he is doing fast, so there is no result. It doesn't mean that the whole work would be done in a few minutes. No, I'm slow. So basically, all the things are depending upon me. Whether you are doing your work, whether you are up to the mark, but it doesn't mean that the product would form on time. This is why always the rate depends on the slowest step. The rate depends on the slowest step. Okay, so that's why in the slow step you have only one molecule. That's the thing. This is called SN1 reaction. In the slow step, if you would be having two molecules, I would be saying that this is SN2 reaction. At that time, means that SN1 represents that in the rate determining step, we have only one molecule. Okay. So now I have just given a few example. Um, let's suppose it's taking your 200 seconds, and it's taking your 200 seconds, and it's taking your 0.01 second. So ultimately, it would not affect your overall rate until or unless you're going to change the concentration of OH negative ion. It's not going to change your result. Minute change, like it's negligible. It was 200, so after addition of this, it's 201. So that's why we are saying that OH with respect to OH minus, this is zero order reaction. The rate is not changing upon the concentration of OH negative ion, basically. Okay. Same goes with this. Same goes with this. Okay. Now, the thing is that we have to propose the mechanism. We have to propose the mechanism. If you can see that this is your full equation, overall equation, and you have to propose the mechanism. If you have noticed, if you have noticed that this was your overall equation, okay, this was your overall equation. Can you see in your overall equation this is not present? This is very important concept, you know. Can you see that uh like there is no any carbonyl carbocation in your main equation? No, this is not. This is absent. So this is called intermediate ion. This is called intermediate. This is called intermediate. Okay. So it should not be present in your overall equation. So ultimately, whenever you're going to propose any mechanism, so it needs some, it involves in the formation of intermediate. So obviously it's an idea. If I'm going to give you an overall equation, I'm going to ask to propose the mechanism. So what you are going to do in the first step, I would be doing this when nitrogen monoxide is going to react with bromine. So this would be formed NOBr and Br. Ultimately, this is we have to form, but Br is not present in your overall equation. So this is your intermediate in this case. So intermediate should be cancelled. So in the next equation, it should be present so that I can cancel. So that I can cancel. So then NO would be reacting with Br to form NOBr. So that would be cancelled, and the remaining would be 2NO, 2NO, then Br2, and then 2NOBr you would be having. That's it. This is the proposed mechanism. This is the proposed mechanism. Okay. So that's why this is the reason. Now I'm going to write the rate equation. As you can see that, rate is directly proportional to NO and Br2. NO and Br2. So as you can see that NO is depending upon, or you can say Br, is depending upon Br2 and NO. So I'm going to replace this. I'm going to replace this with NO and Br2. So I have written NO and Br2 rather than Br, because Br is depending upon these two. Okay. So all in all, it would be NO raised to the power 2 and then Br2. That's called the rate equation. According to this equation, we can say that it's second order with respect to NO and it's first order with respect to Br2. Okay. So you have to do this. Can you write down the can you propose the mechanism of this? This is your main equation. This is your main equation. Yes, you have to show the intermediate as well, okay? Done?
So can you solve it?
See this. After looking at the main equation, okay, so you can see this. When NO2 is going to react with NO2, it's forming NO3 and NO. And when NO3 is going to react with CO, it's going to form NO2 and CO2. Since they are going to be cancelled, okay, and they are going to be cancelled, so the remaining would be NO2 and CO and then NO and CO2. It's an idea basically, it's common sense, it's common sense. After doing 3 to 4 questions, you would be getting an idea that what you have to do. First of all, this is very important that you have to write down any one intermediate so that you can cancel. So that you can cancel. So same goes with this. I have cancelled basically. Now you can see this is your main equation. This is your main equation. Can you propose the mechanism? This is your main equation. Just try this. Okay. Have you done this? Yes.
Yes, sir.
Okay. So what did you write? See this. First of all, in step number one, I'm going to react ICl with H2. They are going to form HCl and HI. Obviously, HI is not present in your main equation. I am considering that this is your intermediate. In the second equation, it should be present so that I can cancel. And then again, I need one more ICl. So again, I would be including one more ICl. They would be reacting to give you HCl and I2 ultimately. HCl and HCl would give you 2 HCl. ICl would give you 2 ICl. Again, the same thing, you would be getting the main equation. That's it. Okay. Are you getting this?
Yes, sir.
Now see this, try this. Again, the same thing, but you need to try this. Hopefully you will do this now. Fast. Yes, done.
So can you show it?
Now see this. You can also do in two steps. See this? We did in two steps. You can see this. Okay, so let's suppose this is your equation. Okay. In reality, the mechanism may be different, obviously, uh, but we can predict the perfect mechanism. But I'm not saying that it would be 100% correct. Remember. Okay. So, and also you can see I have given you again the main equation. Then you have proposed the two equations just like that. Cl minus is present, but this is not present in your main equation. This is your intermediate. That would be cancelled, obviously. And if you're going to add them together, you would be getting the same equation. Okay. This is from the past paper. I have taken this from the past paper. Now you can see in this way, he generally asks regarding the mechanism. Like they are saying that the equation for the reaction between ClO2 and F2 is shown. The mechanism for this reaction has two steps. Okay. Suggest equations for the two steps. Stating which of the two steps is the rate determining step. Okay. So I have proposed in this way. And also in this question, they have given you the rate equation, which means that this is for the rate determining step. So after looking at this, I have made one equation. ClO2 then F2, it would be making ClO2 F2. But ClO2 F2 is not a part of your main equation. So it should be over there so that they can cancel each other. And as a result, you would be adding them together to get your final equation. Okay. So if you would be practicing, so the things would be getting easier for you. This is common sense. Doing mechanism is the common sense, I think. So then see this. Then see this. We would be doing past papers, right? We would be doing past papers. We did these questions in the last class, okay? I'm not doing again. Uh, they are asking the mechanism. Can you do this? This is from the past paper. They are asking, draw the mechanism showing the structure of the transition state. This is from AS completely. This is from AS, man. I'm sending you these notes, okay? You're supposed to do this afterwards. Again, the same thing. See this? What information does this rate equation give about the mechanism of this reaction? A lot of questions you would see, a lot of this is for the catalyst, you know. This is the last part of this chapter. Catalyst. The types of catalyst, homogeneous and heterogeneous. Homogeneous means that when your reactant and your catalyst have in the same state. When your reactants and your catalyst are in the same state, so you can say that this is your homogeneous catalyst. But if your uh, catalyst and your reactants are not in the same state, so you can say that this is your heterogeneous catalyst. That's the difference between homo and hetero. If you remember, you used to do Haber and contact process, right? You used to do your Haber and contact process. In the Haber process, iron was your catalyst, right? In the contact process, V2O5 was your catalyst. So the whole thing was gas, but the iron is solid. Ultimately, this was your heterogeneous catalyst, okay? So then you have to write down how homogeneous catalyst works. In your esterification, acid is used as a catalyst. Ester is aqueous, acid was aqueous, alcohol was aqueous. Sulfuric acid you are using as a catalyst in the esterification is also aqueous. All lie in the same phase. That's why this is homogeneous catalyst. Okay, that's why this is homogeneous catalyst. So you have to include this equation again. Okay, so this is very important reaction. Whenever peroxodisulfate is going to react with iodide, technically they should not react with each other. If you are asking why, because they both have a negative charge, they're going to repel each other. They're going to repel each other. Okay, so means that uh they will be repelling each other after the collision. So their force of repulsion should overcome, should be overcome by you. You have to apply a lot of energy so that they can react. They can react. But obviously, uh, without this, that you are going to provide extra amount of energy, you need to use a catalyst. Iron 3 plus is used as a catalyst. Okay. So when you are going to add iron 3 in this, basically iron 3 would be converting this iodide ion to I2, and itself it would be reduced. And then in the second step, iron 2 that is formed, it would be reacting with this and would be converting into iron 3 and then SO42 minus. So you have used iron 3 that was a catalyst, it's regenerated again and it forms a product. This is the product and this is the product. So ultimately, according to the definition of catalyst, it's regenerated in the end of reaction. It regenerates itself. Okay. What the iron did, it is regenerated after the reaction, but it has given you the product. If you are not going to add your catalyst, ultimately, this reaction is very slow because both have a negative charge. They need a lot of time, so that they can overcome the force of repulsion and they can form the product. So that's the reason you are going to add catalyst. If examiner would be asking how the homogeneous catalyst works, so he would be asking this mechanism, and then you have to write it down. Okay, it's very simple. So that's it for the kinetics. Inshallah, next class would be all in all on the past papers. We would be doing a lot of past papers. Then, if you want to revise any other chapter, then we would be revising. Otherwise, we would be starting paper 5. Okay. Okay.
Okay, sir. Can you send the notes for this
Yes, I'm
chapter?
going to send the notes. Okay, ji. Assalamu alaikum.